minimum cost work in a weighted graph. So the description is so long, let me just explain it. Actually, it's really easy to understand. We are giving n vertices, so n going to be 5. It means the vertices is going to be starting from 0 to 4. And as this just means 0 to 1, it's going to be bidirectionally connected. 0 to 1 with a weight of 7, 1 to 3 with a weight of 7, 1 to 2 with a weight of 1. And we are also giving a queries array. So for the query is that just to check, for example 0 to 3, it's just to check if we're gonna just what to check if node 0 is connected with node 3. So they are connected, and then we're gonna check the sorted path. So the sorted path is defined with the add operations of all as is. So for example 0 to 3, we're gonna have something like 7 and 7 is going to be 7, but it's not the shortest. But we can go it like this: 7 with 1, 0 to 1, 1 to 2, 2 to 1, and 1 to 3. Yeah, this means we can go to some duplicate as this, it doesn't matter, because according to the description we can do that. Yeah, so actually we can go like 7 and 1 and 1 and 7. So the final result is going to be a 1. 1 going to be the smallest number, so we're going to return a 1. If there's no distance, if they are not connected, for example 2 and 4, if they are not connected, so definitely we cannot find, so we're going to return a negative 1. Yeah. So the easiest way to solve the problem, I think, is going to be the unified. Yeah, first of all, we just need to connect them together. So if we are checking 3 and 4, they are not connected, so we're gonna return negative 1. So what about others, 0 to 3? How can we check 0 to 3? Yeah, so instead of traversing the graph like 0, 1, 1 to 2, 2 to 1, 1 to 3, actually we can use the add operation. Actually, it is just the add operations of all the connected components. Yeah, so for example, 0 to 3, the answer is gonna be 1, because the connected component is gonna be gonna have the address of 7, 7, and 1. We just need to use the add operation, and the final result is gonna be 1. Yeah, if we are checking like 1 to 3, it's still gonna be the same result. Yeah, because 1 can go to 0, 0 to 1, 1 can go to 2, 2 to 1, and 1 to 3. Yeah, and the distance, the smallest number gonna still be 1, because they are all connected. Yeah, this is why it's gonna make the problem a little bit easier. Although from the examples we cannot find that, but actually, yeah, if we are giving more examples, maybe it's more straightforward. But we are not giving such kind of examples. But actually, the idea is that we just need to use the add operation. Yeah, so for example, node 0 with 3, we're gonna use the add operation to add all of them. So they are connected, and the smallest distance is going to be 1 by the add operation. Now let's just try to use the unified to solve the problem. So I'm going to prepare a template of unified. So from the init, it's going to be the self with the node, and the self.parent gonna equal to list with the range of n means the number of the node. And then I'm going to prepare a self.add array. It's going to be negative 1 times n. And this is similar like a array, but here, as we are using the add operation, so this add array going to store the add operation of all the nodes. This is going to make the problem a little bit easier for us to solve. Yeah, we just need to find the parent node, and we're going to add all those numbers to the parent node, and then we can solve it directly. So for example, if the parent node is 0, we're going to add all the values to this parent node, so it's going to be a 1. It means 7 add 7 add 1 is going to be 1. So if we are checking node 3 with 0, yeah, we can directly check find its parent. So for example, we can use the unified 3. It's going to be this 0 node, and its value going to be 1. We can solve it directly. This is why we're going to use a self.add array. Now let's just define the unified. We need to use a find while n not equal to self.find with yeah, let's just use this while n not equal to self.parent n. So n gonna equal to self.parent n. And finally, we're gonna return this node n. And now let's just write the union. Self with n1, n2, and weight. Yeah, because here we just need to check the weight. So for the union, we're gonna prepare two parent. It's gonna be self.find with n1 and self.find with n2. And which one gonna be the parent? It doesn't matter. So for example, let's just say p1 gonna be the parent. So self.parent p2's parent gonna equal to p1. Yeah, so this is just the union. But currently we didn't use this self.add array. Yeah, and we need to accumulate to the add array. So self.add which one? Parent, it is p1. Yeah, so we're gonna use the add operation. We're gonna add the weight, and then we're gonna add the we're gonna add the p2. So self.add with p2. Yeah, so we're gonna add all of them. So we're gonna accumulate all those weight to p1. For example, we're gonna accumulate all the weight to 0. Yeah. So for n1, n2, for example, it is 0, 1. We're gonna accumulate this 7 to p1. Yeah, now let me just start coding for the final answer. So we're gonna use prepare unified. It's gonna be uf with n, and then I'm gonna check all the edges. So maybe uv and w inside the edges. So let's just union them together. uv and w. Yeah. Now let's just check the final result. Let me set it to -1 times the length of the queries. So for ab in let's just enumerate all the queries. If uf.find a equal to uf.find b, this means node a and b gonna be connected. If they are connected, we need to check the final result. So here we're gonna use uf.add, and inside we're gonna use uf.find with this node. Yeah, here a or b, both of them should be okay. Finally, we're gonna return the final result. Yeah, now let me just run it. As you can see, it works. Now let me just submit it to Stack if it can pass. Yeah, it might be a little bit slow because I didn't speed up, but let's just have a check if it works. Maybe it didn't. I'm not sure. Yeah, as you can see, it didn't work, but we can speed up from the shortcut of this find. Yeah, so we're gonna speed up from here. So self.parent n gonna equal to self.parent inside is gonna be self.parent n. So this is gonna be a shortcut of the find. Otherwise, it's gonna be much slow. Yeah, now let me just submit it to check if it works. Yeah, you can also prepare a racking to speed up a little bit. I mean, we're gonna make the unified a little bit. We're gonna make the graph a little bit balanced and to speed up a little bit. Oh, it still didn't work. Yeah, I thought it would work, but it didn't. Yeah, this is I did something wrong. This is not double equal, it is a single equal. Now let me start to submit it again. Yeah, now as you can see, it speed up a lot, only with one line of code. Before we didn't work. Now we increase speed even to 0.1 seconds. Yeah, so this is why for this file we're gonna speed up, we're gonna shortcut it. Yeah, by using this line of code, self.parent n gonna equal to self.parent with self.parent n. Yeah, so this means normally how we gonna find the parent node? We're gonna find one. So for example, this node to this node, and to this node, and this is the parent node. But for this line of code, we can jump from this one directly to the parent node. This is why we're gonna speed up. Yeah. And another thing is about here. Yeah, so the time complexity is gonna be n log n. N is the length of the queries, and for each of the query, it's gonna be another log n time. Yeah, another difficult part is about this line of code. Yeah, so this line of code is just to accumulate all the values to its parent. So first of all, we're gonna have this self.add p1. So p1, because p to its parent is p1, so p1 gonna be the parent. But what we're gonna do? We're gonna accumulate all the values from this weight. Let me use another color. So this 0 is p1, and this 1 is p2. First of all, we're gonna accumulate the weight to p1. p1 we're gonna set it to -1. It means for binary bit it's gonna be 111, and 111 at 7 is gonna be 7. So we're gonna accumulate its weight 0 to 1. Yeah, because its weight is w, so we're gonna accumulate its weight, and then we still need to use add with the self.add on p2. Yeah, because inside this this node, it might be another value. Maybe it is not -1. It might be some other values. Maybe this value is the end of this value at 3. Yeah, let me make it clear. Yeah, because here is a little bit difficult to understand. So currently we are checking node 0 and 1. So we're gonna accumulate this weight. This weight is here. Yeah. But what about this one? This one can be a -1, but what if it is not -1? Maybe this 1 and 3 has already been connected. And inside, what's gonna be the value? So the value gonna be -1 and 7 and -1. It's gonna be a 7. Yeah. So what about this 2? 7 and 2 at this node 2. So it's gonna be 7 and 1 and -1. It's gonna be a 1. So actually inside here it's gonna be a 1. Now if we are checking the node 0 to 1, or what's gonna be the final result? It's gonna be 1. Yeah. And similarly, if we are checking 0 to 3 for this example, yeah, because the parent of 3 and the parent of 0 is this 0 node, and the self.end with 0 it is 1. So we can directly return the 1 because it is connected and we can get it directly. Yeah, and also for here, if this uf.find a equal to b, this means it is connected, we can get it. Otherwise, if it is not connected, we're gonna make it a -1. That is why we prepared the result array as -1. Yeah, I think that's all about it. Thanks for watching. See you next time.